In this tutorial, we'll be discussing the types of aqueous solutions and solubility. So what happens exactly when a solute dissolves? Well, first of all, there are attractive forces between the solute particles holding them together. So if we take, let's say, a grain of salt, there's positives and negatives in here that are keeping them together. There are attractive forces between the solvent molecules. So let's say we have water. There's charges in here, or other attractive forces that are keeping those together. When we mix the solute with the solvent, there are attractive forces between the solute particles and the solvent molecules. If the attractions between these particles are strong enough, they will dissolve. For instance, here, the sodium is a positive. The oxygen here is partially negative because it's electronegative. There's an attraction between these two. That attraction is actually strong enough to pull it away from the solid. Each ion, so table salt specifically, each ion is attracted to the surrounding water molecules and pulled off and away from the crystal. So oxygen is electronegative. It wants more electrons, which is making it partially negative. It's surrounding that positive, and it pulls it away. And same over here. The hydrogens are partially positive because it's less electronegative, and the electrons are being taken away by the oxygen. And it's attracted to the negative of the chlorine. When it enters the solution, the ion is surrounded by water molecules, insulating it from other ions. The result is a solution with free-moving charged particles able to conduct electricity. Remember, electricity is the movement of electrons. In order for electricity to be conducted, those electrons have to be moved. These charged particles is like giving the electron more mobility. So electrolytes versus non-electrolytes. Materials that dissolve in water to form a solution that will conduct electricity is called an electrolyte. Materials that dissolve in water to form a solution that will not conduct electricity are called non-electrolytes. In order to conduct electricity, a material must have a charged particles that are able to flow. Electrolyte solutions all contain ions dissolved in water. Ionic compounds are electrolytes because they dissociate into their ions when they dissolve. Dissociate just simply means they break apart. Non-electrolyte solutions contain whole molecules dissolved in the water. Generally, molecular compounds do not ionize when they dissolve in water, with the notable exception of acids. So let's take a look at salt and sugar. Salt, or ionic compounds, dissociate into ions when they dissolve, so there's positives and negatives all over the place. Sugar, however, or molecular compounds, do not dissociate when they dissolve. Notice there are no charges in these clusters. Acids are molecular compounds that ionize when they dissolve in water. In other words, ions are formed. The molecules are pulled apart by their attraction for the water. When acids ionize, they form H+ cations and their anions. The percentage of molecules that ionize varies from one acid to another. Strong acids are acids that ionize virtually 100% of the time. So that hydrogen will almost 100% of the time come off of the HCl. However, weak acids are those that only ionize small percentage. So that hydrogen only comes off some of the time. So let's relate this again to electrolytes. Remember, electrolytes have to have ions because they have to have a way for the electrons to move from one location to another. Strong electrolytes are materials that dissolve completely as ions. Ionic compounds and strong acids are good examples. Their solutions conduct electricity very well. Weak electrolytes, however, are materials that dissolve mostly as molecules, but some ions are in there. These are called weak acids. Their solutions conduct electricity, but not very well. When compounds containing a polyatomic ion dissolve, the polyatomic ion stays together as a cluster. When ionic compounds dissolve in water, the anions and cations are separated from each other. This is called dissociation. Notice we have Na2S. Over here, the sodium and the sulfide broke apart. Because we had two sodiums over here, that's why we have a 2 in front. Unless it's a polyatomic ion like PO4, where there's not going to be any separation here. You got to think of what's the cation and what's the anion in this scenario. When compounds containing polyatomic ions dissociate, the polyatomic group stays together as an ion. So this SO4 is sulfate. When we go to the right hand side, sulfate stays as a cluster. That 4 does not change anything. However, this 2, because the sodium, there's 2 of them there. Think of it as when we put them together. When we put them together, we have Na+1 and SO4 2 minus. And we crisscross. That tells you that we need 2 sodiums and 1 sulfate. That's the same situation here. When a strong acid dissolves in water, the molecule ionizes into hydrogen and anions. So here we have the SO4 is a sulfate. It's over here again. And then we have 2 hydrogens, and those are right here. Remember, that's like saying H and SO4. If we were to crisscross those, we would need 2 hydrogens and 1 sulfate. So let's get some practice with this. Write the equation for the process that occurs when the following strong electrolytes dissolve in water. So this is going to break apart. We have calcium and we have chlorine. Calcium has a +2 charge, while chlorine has a -1 charge. We find those on the periodic table. Or we could crisscross it like that. We have 2 chlorines here, and it's not a polyatomic ion, so there's going to be 2. Here, we actually do have a polyatomic ion. Uncross it, and we have a +1 and a -1. So a hydrogen with a plus, and an NO3 with a minus. We're going to put AQ next to these, because these are all dissolved in water. And that's just saying that it's aqueous. It's dissolved in water. Alright, this one. Uncross it, and we have NH4 +1 dissolved in water, and we have CO3 2 minus aqueous because it's dissolved in water. We have 1 carbonate, and we only have 1, and we have 2 ammoniums. Some ionic compounds like NaCl dissolve very well in water at room temperature. Other ionic compounds like AgCl dissolve hardly at all in water at room temperature. Compounds that dissolve in a solvent are said to be soluble, while others that do not are said to be insoluble. NaCl therefore is soluble in water, while AgCl is insoluble. The degree of solubility depends on the temperature. Even insoluble compounds dissolve, just not enough to be meaningful. So, how do you know when a salt's going to dissolve? Predicting whether a compound will dissolve in water is not easy. The best way to do this is some experiments to test whether the compound will dissolve in water. Then develop some rules based on experimental data. We call this the empirical method. And I'm going to explain a few general rules. So, compounds like Li, Na, K, those are alkali metals, are soluble with no exceptions. And H4 is also grouped in there. Nitrates and acetates are typically soluble with no exceptions. Halogens, Cl-, Br-, and I- are soluble with the exception of whether they're with this. So lead chloride would not be soluble. Silver chloride would not be soluble. So on and so forth. Sulfate is typically soluble unless it's with something like this. So calcium sulfate is not soluble, even though sulfates typically are. Here's another example, but now we're talking about insolubility. OH is usually insoluble. So you'll usually form a solid unless it's formed with like lithium or sodium, then it's going to actually be soluble. Calcium will be slightly soluble, so it's going to dissolve a little. Sulfide, S2-, is typically insoluble unless, once again, Li, K, and H4. Remember that information from the previous slide. Carbonates and phosphates tend to form solids as well, unless, once again, it's mixed with an alkali. So let's determine whether or not these are soluble. KOH. So we look at our rules. OH usually forms a solid unless it's with K. So that means that this is soluble. AgBr. Br is usually dissolves unless it's with the silver. So that means that this is insoluble. CaCl2. Chlorine is usually soluble, and Ca is not one of the exceptions. So that means it's still soluble. Lead to nitrate. Nitrates are usually soluble with no exceptions. So that means it will be soluble again. And then finally, lead to sulfate. Sulfates are usually soluble with the exception of lead. Therefore, this is insoluble. And that's how you use the solubility chart.